Hey,
Hi, Chris. How are you doing today?
I'm good.
Super
So
early
yeah,
for you,
you're
I
dead
presume.
right about Hayward Heath. That's where I am.
Oh, yeah. So I did get it right. Amazing, amazing, fantastic. So, as a quick introduction, Chris Swan is one of the big brains behind the ad company, and he's one of the people who is now responsible for making the internet a much more safer place. Shout out to the ad company; those people are brilliant, and we love them. Also, I mean, I would love for Chris to, if you could tell us a little bit more about what the ad company is and what you guys are all about.
Yeah, sure thing. I'll get to that in the presentation. So
All
go
right.
away.
Got it. Got it. Also, I did come across the fact that you are a co-host of a podcast of your own called Tech Debt Burn Down. Is that
That's right.
is that what it's called? Yeah, and you co-host with Nick Selby. So could you tell us a little bit more about that?
Sure thing. So it's a podcast about technical debt and how people deal with technical debt. We've had um, sort of 10, 11 guests on it now, talking about various different aspects of tech debt with security, tech debt with observability, tech debt with things like software bill of materials.
Mm-hmm.
And so actually we'll be dropping, I think, the software bill of materials episode tomorrow. Um, my yeah, I guess I'm not supposed to pick favorites, but the recent one we did with Charity Majors on observability is absolutely fantastic. So highly recommend that if people want to kind of dip into an episode, try it out.
Mm-hmm. Well, shout out to the Tech That Burn Down podcast as well. Go check it out. It's everywhere. You can find it on Twitter. Just follow the account, search it on Twitter, and you'll find it. It's pretty easy to get to. Anyway, so Chris, I'll let you have the stage and tell everybody what's going on today and what you're here to talk about. And
Thank you very much.
yeah, take it away.
All right, so share my screen, and um, I'm going to be talking about Dart on ARM. And so let me just complete the introduction. So, as was already said, I'm an engineer at the App Company, and we're building a platform that puts people in control of their data. I'm co-host of the Tech Debt Burndown podcast, and also a cloud editor at InfoCube. So I write there about cloud DevOps, certain security things, and various stuff around performance. Uh, links to Twitter, LinkedIn, etc. You'll find all of those at chris.swans.net. So all of my various social media profiles are there. So here's what I wanted to kind of take folk through today. I'm going to start out with why ARM is important. And that really comes to this notion of full stack Dart to complement Flutter apps. So Google's been pushing pretty hard on this idea that if you're developing a mobile, web, or desktop application using Flutter, then you're learning Dart to do that. And why not then use Dart to write the APIs for the backend? And then the other piece to the puzzle is ARM growth in the cloud and the Internet of Things. And I'll show you some charts of just how huge that's becoming. So, I think we're all very used to using systems based on the x86 architecture, but the growth of ARM is really big right now. And I think that means that we've got to factor in how we're going to use ARM in the future. So Dart has two ways of running the code. We can use just-in-time compilation in the virtual machine, and we can do ahead-of-time compilation. So I want to briefly look at the various trade-offs between those two things because it kind of factors into how we build things to run on different platforms. I'm going to touch upon the dependencies for building and running ahead-of-time binaries because that's a big piece of why we need to treat different architectures differently. And kind of everything by default is set up for x86. So how do we get from that x86 default to being able to build things for ARM? And then, kind of wrapping up, I'll show how we can make cross-platform building very easy. So we can have automated systems that are going to build things for x86 and different flavors of ARM all at once. So no need to kind of be kind of manually stepping through, let's first build it for x86 and then build it for ARM v8 and then build it for ARM v7. It can all be done at once. And hopefully some time at the end for questions. So starting off then with full stack Dart. At the recent Google I/O event, a lot of the talks that were focused on Dart were actually focused on this idea of full stack Dart. So there was an Ask Me Anything on Cloud Dart and full stack Flutter, and then also a set of talks on full stack with Kotlin or Dart on Google Cloud. And in many cases, that was encouraging people to use Dart and Google Cloud Functions or Google Cloud Run in order to provide the back end to Flutter applications. Google have also done a podcast on this, a recent episode of the GCP podcast, just called Full Stack Dart. And that was with Tony Pugels. And Tony is one of the core Dart SDK developers at Google. So I see his name popping up pretty frequently. He's recently spearheaded the work for the Dart official image in Docker, which I'll be touching upon in just a moment. So, as I said, the other piece to this puzzle is ARM growth. And ARM growth is huge in the cloud. And ARM is, I think, already the predominant architecture that's in use by devices for Internet of Things. So a little while ago, Amazon launched a new range of instances using their own silicon based upon the ARM architecture. And that recent release they call Graviton 2. There was an earlier Graviton, which was just Graviton. It wasn't Graviton 1. But I kind of, in retrospect, we might call it Graviton 1 now. And looking back over 2020, we can see that Graviton accounted for 49%, so almost half of the instance additions to the AWS environment. And so very quickly, we can see that it's becoming kind of the dominant strain, if we could use that terminology, of instance within Amazon Web Services. And that really comes about for a few reasons. One is price, that because Amazon's using its own silicon here, it can offer that at better price points, but also performance. And so the performance from these new ARM-based instances is really good. And I think seeing similar thing in the cloud there to what people getting the new M1-based Macs are seeing with the performance of those. And so then the overall price performance equation of ARM in the cloud becomes pretty compelling. And then there's the Internet of Things. So this is a picture of a Raspberry Pi Model 4, so the latest version of the Raspberry Pi. This has a 64-bit ARM v8 system on chip on it. And these kinds of devices, whether they're being used by hobbyists to try things out, or whether they're kind of going into compute modules or fully integrated systems, are what we see in just about everything running on the edge for the Internet of Things. And so, server class hardware, but in a really small package with a really low power consumption, where we can run things very close to the sources of data that we might be capturing in, say, an industrial environment. So in the intro, I was asked to talk about a little of what the @Sign company does, and this I really want to focus on. Why are we interested in ARM? So at the company, we're building the platform, which is a platform for privacy-preserving applications. And there's really two very simple components to this. So a root server is almost like a DNS server, and that gives people a place where they can look up one of our identities, which we call an @sign, and find the infrastructure associated with that. And that infrastructure we call a secondary server. And these secondaries are essentially uh, a private server that people have in the cloud where they can store their data and have fine-grained control over how applications have access to that data and how that data is shared with other applications. And we call these things secondary servers. So one of the things we do at the App Company is we run secondary servers, and so we've got a whole bunch of those running on top of Google Cloud. But we also want to give people the flexibility to run those secondary servers wherever they want. So something we recently launched is the distributed edge secondary server, or DES. And people can run that on a cloud virtual machine or a Raspberry Pi or any other kind of device of their choice. And so part of why we want to be able to support ARM is give people the choice, not just between running on our service and running where they want, but when they choose run where they want, then they have the choice between x86 or ARM, whether that's in the cloud or a physical device that they're managing for themselves. And of course, we want to have those choices as well. So, at the moment, Google Cloud is purely x86, but we might want to be able to run some of our secondaries on other clouds like Amazon, where ARM is starting to really gain traction. And we also want to be ready for when Google starts having ARM in their cloud as well. So I said I'd talk a little bit about just in time versus ahead of time and the various trade-offs that we have between those different approaches when we're using Dart. And I'm going to illustrate this with a really trivial application that I've got here that I call Dart Show Platform. And it's just a slightly more useful kind of a hello world. And so the source code for the application is in this top box, and it's just literally a handful of lines of code. And the key line here is this print platform.version. And the output that we get from that is shown at the bottom. And this is very similar to what you would see if you ran Dart minus minus version. And so when you call Dart minus minus version, it's essentially printing this platform version information. So it's giving us some pretty useful stuff here. So it's first of all telling us the version of the Dart SDK and which channel we're using. It's telling us when that was built. And it's also giving us information about which architecture that command has just been run on. So when I copied these particular output snippets, I was running at the time on a Raspberry Pi 4 with Ubuntu, which is a 64-bit operating system. And so it's telling me that it's running on Linux ARM64 there. So with just-in-time compilation, I can just use Dart run and take that source code and run it in a virtual machine. And so on my command line here, I've started off with time, so it's telling me how long things take. And then I've just done Dart run show platform.dart. So that source code that was on the last slide. And it's given me that output. And it's telling me that it's taken about 5 seconds in order to run that, which is a pretty big chunk of time. We wouldn't want users to be waiting 5 seconds all of the time in order to get something as trivial as that version information. And that kind of shows the overhead of starting up the virtual machine in order to get our output. So in order to get past that overhead, what we do here is use ahead of time compilation. And so if I, instead of saying Dart run, say Dart compile exe and feed my source code in there, then it's going to create an executable for me. And by default, that'll be called show platform.exe. And I can run that again with time. And we can see things that are much better here. So it's taking 23 milliseconds instead of almost 5 seconds. So orders of magnitude faster. And this is really the approach that we're going to use for something like Cloud Functions, because we want a cloud function to be responsive when we're calling it from a mobile application in order to get the answers from that function back to the mobile app and the user making use of that mobile app as quickly as possible. So ahead of time compilation gives us very quick startup. Um, but the trade-off there is we're not able to observe the application running in its virtual machine over a long period of time. And so we miss out on some of the optimizations that we can get from just-in-time compilation over the longer term. Another part of the trade-off is compilation is slow. And so if I time how long it takes to actually do that compilation, I can see it's taking about 20 seconds here. And so that means I don't want to be compiling stuff all of the time. I want to be doing my compilation as I'm preparing a function that I'm going to run in the cloud. Um, and then the user is never having to wait for that. So moving on then to the dependencies for building and running an ahead of time binary. Well, if I was to package up my trivial application here using Docker, then I can use a two-stage Docker build approach. So the first stage, I can be using the new official Dart image, and I say use that as build, which I use later on. And all I'm doing here in the next few lines is saying a working directory of app, copying in my source code, and then running .compile exe on that source code with an output file of .show platform. Now, the second part of that build, I'm then moving on to using the from scratch pattern. And scratch is an empty image in Docker, which means that I can have things really small. And with other languages like Go, it's possible to create a statically compiled binary and just copy that binary into a scratch image. And that's all we need. Now, Dart isn't a language that offers statically compiled binaries. Part of the philosophy of the language is to use a dynamic runtime. And so what I need to do first here is copy in that runtime environment. And then with that runtime environment at my disposal, I can then copy in the binary that I created in the first stage and define that binary as my entry point. And so this gives me a little container that I can use to wrap around my application. And that's the kind of thing I could deploy into Cloud Run in order to serve as an SDK or something like that. So if I take a look at what's inside of that runtime, then these are the library dependencies that are kind of the minimal part of what I need for Dart. And so, what do we see here? So networking, SSL, libc, libdl, libm, libnss, which is for naming, pthread, resolve, which again is for network, and RT, along with the platform specific libraries, and then lastly the certificates. And the final part of this is just copying all of those into place for the runtime. So all of that works for x86, but how do I get ARM? Well, what we've done at the app company is create our own build image, which is essentially our fork of the Dart official image. And inside of that, we've created some conditionals that allow us to detect which platform we're running in, and then make use of the architecture specific pieces of those different platforms. So you can see we're starting out here with a case statement that's based upon uname minus m. And uname minus m is going to tell us which hardware platform the operating system is running on. So there's three possible outputs here that we're dealing with. So the first is ARM v7, so that's 32-bit ARM processors. The second is AArch64, So that's 64-bit ARM processors, so V8 and V9. And then lastly, we're kind of catching x86 as the default and having the architecture there. And all of these other blocks are just copying in the platform specific libraries for each of those. And then having captured that architecture label, we can then just use that as part of the environment to then copy in all of the generic pieces that we need in runtime. And so, the rest of this is kind of similar to um, the set of libraries that we were copying in before. It just puts in the specific architecture libraries, whether that's ARM v7, ARM v8, or x86 as appropriate. So at this point, we can make cross-platform building very easy. And so, here's the Docker file now for the same Dart show platform. And the only thing I've changed is instead of having from Dart, I've got from @company build image, because this is using our cross-platform fork of the build image rather than the Google Dart official image in Docker. And I expect in not very long that official image will also get ARM support, and I'll then be able to drop having to have a fork, and I'll be able to just do from Dart and expect to get that cross-platform support directly from the official image. So if you look in the GitHub issues for Docker, there's already a conversation happening with people like Tony Pugels about that topic. And it's clearly something that people at Google even are interested in and are working on. If I then move on to using GitHub Actions in order to build things from these Docker files, then here's a snippet, which is the build and push section from my GitHub action. And this is making use of my Dart show platform Dockerfile, which was on the last slide. And in order to get output for multiple platforms, all I need to do in this final section here of platforms is list out the platforms that I want support for. So I've got Linux AMD 64, which is my x86 builds, and Linux ARM 64 V8. I'd note here that as I've talked through this, that's now 3 different ways that people have of talking about the different platforms. So, sometimes we're talking about ARM 64/V8, sometimes we're talking about ARM 64, sometimes we're talking about AArch 64. And this is just one of those naming issues in the industry that we have to live with, that people use different names for the same things in different contexts. And so our code needs to be kind of correctly using those in the appropriate contexts. So here's the end result. These are some screen grabs from the @company repos that we have on Docker Hub. And so these are the automated builds for that trivial Dart show platform application that I've been using it as an example here. And what we can see is, the ARM version is really, really small. So that gives us a 3.6 meg binary image. AMD 64, the x86 version, tends to be a little bit bigger, generally, about 0.9 of a meg bigger. And that's just larger libraries being carried around. So that's all well and good for a trivial hello world with a bit of platform information application. But what about a real application? So on the right here, I've got a real application, and the sizes are being obscured by my video image. But our secondary server that I was talking about earlier on, and so a core component of our overall architecture. Um, with this approach, we can get a 5 meg image for ARM and a just under 6 meg image for x86. And so that gives us a really small image which makes it very easy to kind of deploy that out to edge locations, and gives us kind of minimal latency whenever we're having to update that in a production environment. So to recap, then, uh, ARM is important for two reasons. The first is because full stack Dart gives us a great way to complement Flutter applications by building Dart applications to implement APIs on the server side. And ARM growth is huge in both the cloud and on the Internet of Things. Dart gives us a choice between just-in-time compilation and ahead-of-time compilation, and there are trade-offs there in terms of performance. But for things that we want to start up quickly, then ahead-of-time compilation is the way to go, and that's generally what we're asking for when we're doing things like Cloud Functions. And so then, there are various dependencies that we have to have for building and running those ahead-of-time binaries, and in order to provide those different dependencies, we can take what has been done for x86 with things like the official Dart Docker image, and create multi-platform approaches of that in order to get ARM support. Once we've got that ARM support into the underlying build images, that then makes cross-platform building very easy for us. Which now brings me on to some time for some Q&A. So I've seen some questions appearing in the background. I will move on to answering those.